The first one will be given by Professor Harald van Brummelen. He's the director of the Multiscale Fluid Dynamics Institute at Eindhoven University of Technology in the Netherlands. He obtained a PhD degree in 2001 after having conducted doctoral studies at the Center for Mathematics and Computer Sciences of the University of Amsterdam. After a 2 years period as a postdoc from 2001 to 2003 at the Department of Aerospace Engineering at Delft University of Technology, followed by a 5 years period as an assistant professor at the same department and a short associate professor at Delft in 2009, he was promoted to full professor at the Department of Mathematics and Computer Science. Boltzmann equation, moment closure approximations, and goal-oriented error estimation and adaptivity. The topic of this lecture today is towards adaptive multiscale techniques for kinetic theory. Professor van Brummelen, the floor is yours.
Thank you, Professor Mann, for this kind introduction, and also thank you for the opportunity to present this work here. It looks like we're going to have a very nice session on talk. We're not there yet. We're on our way. That's what I'd like to say. Maybe as a sort of an initial question, so who's familiar with kinetic theory? Then I always pose the complementary question, so who is not? Okay. Yeah, so it seems that actually kinetic theory is sort of a new field for our community. And I think it's interesting because I have the impression that as a community we can make a big impact there. Then I will talk about the structural properties of the Boltzmann equation. So Boltzmann equation is sort of the prototype kinetic equation. It has marvelous structural properties, and you need to understand those if you want to see what multiscale paradigm is. Then I will talk about moment closure approximations, which is actually a sort of old approximation technique, but a problem occurs that in many applications it's really not so clear what the Knudsen number is. So it may be not unambiguously defined in the sense that now it refers to a characteristic length scale, but in many systems you will not have that available. Your system may have many different length scales. It's not clear what would be a characteristic one. It may not be fixed in the sense that you have transient behavior, and I will show an example of that in a moment. Or you may be in the intermediate regime, so you're somewhere over here. And then at the same time you also have transient behavior. And the aim in this system would be actually to do a temperature equilibration, so you want to understand the heat transfer in the system. So this would typically be an application where you would need to turn to kinetic theory. So when we started this project, I think it's also good to talk a bit about the years that you do going through such a process. So when we started this actually some 8 years ago, it started off as a twisted to continuum project. So what we were intending to do was actually to couple Navier-Stokes-Fourier dynamics. So that means that say it's a micro-macro adaptivity. So the macro scale model would be the Navier-Stokes-Fourier. Micro scale would be molecular dynamics. And what we intended to do is actually to do semi-rigorous model adaptivity. So based on a posteriori error estimates. Now one of the first questions. Okay, so this is actually the aim. So we started off with what you could call a type A, mainly multiscale modeling strategy. based on a posteriori error estimates. So essentially you would divide the domain in two parts, one where you apply a continuum model, another part where you apply molecular dynamics, of course, unique, and then you identify where you apply the molecular model based on an a posteriori error estimate. But now a few fundamental questions occur. So if you want to do this based on a posteriori error estimates, then the first thing that you need to answer is how are these models actually connected? So how is molecular dynamics connected to the Navier system? Now for solids, I think you could revert to something like quasi-continuum to connect the molecular model to a continuum model, but for fluids it's really not so clear. The second thing is that how would you actually construct an a posteriori error estimate? So the basic thing that you would need to have for that is to be able to evaluate residuals of your micro model given the solution to the macro model. So if I solve the Navier-Stokes-Fourier equations, in which way does that actually constitute an approximation to molecular dynamics? I plug this solution into my molecular dynamics system. I really have no idea. Similarly, so what are the transfer operators, or indeed as pointed out, the micro residual evaluation? And finally, something that you would, the question that you would I can compute it. And for this system, you really have to wonder whether that's the case. The 19th century. So we know what to do. And that's actually when this project transformed into adaptivity for kinetic equations, because basically if you want to connect these two models in a rigorous way, you need to be able to do adaptivity for the kinetic model. So what's Boltzmann's equation? Boltzmann's equation is an equation for, it's a molecular model, it's an equation for individual molecules, but for a probability distribution. So it's a scalar equation. F in here represents probability density. And what it represents is actually, so it's probability density defined on position momentum space or position velocity space. The velocity which appears over here, transport velocity, is an independent variable, right? So it's not a standard transport equation. This velocity, R3 refers to velocity. So it's set in a 2D plus 1 dimensional space where the plus 1 accounts for time dependence. It consists of two parts. So the first part is the transport part, so the dTF plus Vj dxfj. It's transport, and then there are collisions, which basically account for molecular interactions. If you were able to solve this equation, then you could extract all your microscopic information from that. So basically, you would be able to get to the fluid mechanical description, rho, which is density. You could compute rho u as an integral, or as a moment of it, I should say, which is momentum, and then you could also compute the second moment of f, which gives you internal energy. You can also compute more exotic moments. You can compute stress tensor P, you can compute heat flux tensor, etc., etc. So all these macroscopic properties will appear as moments of your one particle marginal if you can solve it. As I mentioned, so there's also a prototype for other kinetic equations, which makes it really interesting, because these kinetic models have a huge range of applications. You can think of plasma physics, so that would be the Flason Maxwell system, galactic dynamics, chemotaxis, and there's actually a whole range of other applications where this kind of models appears. So just if you want to do this numerically. Well, at first, what I already mentioned, it's set in a high-dimensional space, right? So for a problem in these spatial dimensions, the Boltzmann equation is defined in 2D plus 1 dimensions. So for typically engineering application, D is 3, then we would need to solve a problem in 6 plus 1 dimensions, where as I pointed out, the plus 1 is special because it refers to time. The second thing is that the velocity domain is unbounded, so velocities can range from -infinity to infinity. If if we truncate the domain, then typically general molecular interactions, which really requires some time and effort to implement it. But basically they sort of proposed it, mentioned it, but did not provide any indication of what kind of method you would use to do that. So you can think of what I'm about to present as a type A domain decomposition multiscale method for transition between the Boltzmann equation, which is the microscopic model, and the Euler equations, which is the macroscopic model. It provides a hierarchical model, right? So we do not have two models, but we have a continuous hierarchy of models. And actually, it has the right structure to do a posteriori error estimates. So we do not only know how to refine, but the error estimate will tell us where to refine in a rigorous manner. So to understand that, first something about the structural properties of the Boltzmann equation. So let me emphasize that the Boltzmann equation is really a beautiful equation because of these structural properties. So the first thing, it's a property of the collision invariant, of the collision operator is collision invariance. So basically the integral which is indicated over here for psi, whenever psi is in the span which is indicated over there, right? So it's constants, it's linear in velocity, or it's the normal v squared. And what it gives you, that's maybe more relevant, is it gives you your conservation properties. So if you plug in 1, the constants, then you get conservation of mass. If you have velocity components, you get the corresponding conservation of momentum. If you plug in the v squared, you get mass, momentum, and energy. So that's one thing. The second thing is that the collision operator is entropy non-increasing. So you can define an entropy. Typically, this will be f log f, standard Shannon entropy. And then you can show that this is dissipated by the collision operator. And as a result of that, you can show that the evolution of the Boltzmann equation is entropy non-increasing. Actually, what I should mention is that convergence of the solution to so-called Maxwell-Boltzmann theoretical model and macroscopic models, the fact that you have underlying equilibrium distributions. Finally, some other properties of the collision operator is generally translation and rotation invariant. It doesn't make much sense to go into the details, but what that gives you is actually Galilean invariance of the equation. Right? So any meaningful physical model has to be Galilean invariant. That's what you get from these rotation and basically the symmetry properties of the collision operator. So just summarizing closure approximations, just briefly, I will skip over a few of the details, but essentially what it is, that's basically what brings it to our community. If you reinterpret it, it's a Glerke method. It's not how it was originally developed. Actually, turns out that that's what it is. So we start off with we're going to do a projection. We start off with a finite linear subspace, call it M, which consists of polynomials, right? So constants, linears in v squared, e to the power 3, etc. For convenience, we will store those in a vector, so that's boldface M. These angle brackets to denote integration on velocity dependence. And then basically what we do is it's a two-step procedure. So we take moments of the Boltzmann equation, so we integrate the Boltzmann equation over all the basis functions in this vector. And then what you have is the term which is indicated in blue. These are called the moments. These are moments of the one part of the marginal. The terms called in red are called flux, and the term in green is a production term. And of course, if you do this for a finite number of basis functions, what you can show is actually that you get an exponential distribution. Right? So it's basically it's an exponential, but in the exponential you have a polynomial. So you can give two interpretations to this. The first one would be that its disclosure is the approximation which is closest to equilibrium in the relative entropy. But more interesting interpretation is actually that it's the information theoretical interpretation of entropy shows that it's the least biased distribution that you have given moments. Right? So without any bias, with least bias given the moments, you would have to take this distribution. And then actually, if you go into the literature, the structure was not clear then, but it was on the subspace M that we use. Of course, we want one thing that we do is we at least put our collision invariance in the subspace, because that will give us better conservation properties now in our moment closure system. We have to make sure that M is invariant under actions of rotation and translation. And that basically restricts the subspace to polynomials. You cannot construct this. It's virtually impossible to construct a subspace which is invariant, say, translation and rotation invariant if it's not polynomial. If you choose a subspace which has that, you can construct many ones in different orders, you automatically get your Galilean invariance back. And finally, of course, you have to be able to compute the integrals, which means that you imposes some integrability condition. The reinterpretation of this is actually that it's a Galerkin projection. Now we can see it a bit differently, so we think first introduce. It's not necessary to read this slide in detail. Basically, what you have to observe is you first suggest a renormalization of the Boltzmann equation. So you say, well, let's not approximate f, but let's write f is the exponential of g and approximate g. Right? It's just a rewrite of the equation. And then you make a Galerkin projection in the velocity dependence. So the psi will be a test function, it lives in some space, and it lives in the same spaces where you're going to look for the approximation to g, standard Galerkin approximation. And now we can derive the structural properties of the Boltzmann equation in this system from Galerkin orthogonality. Because basically, 1v and v squared are in our test space. You can just plug them into the equation, the approximate distribution will satisfy that. You automatically get your conservation properties. We have the Galilean invariance by the choice of the subspace that we have. And because, and this is an interesting thing, because of course the logarithm is the inverse of the exponential, if we apply the log to our distribution, we get again just a standard polynomial which fits into our test space, and that gives us the entropy dissipation property. And finally, you can also show that this system will be symmetric hyperbolic, which in principle is an indication of well-posedness. Turns out it's not enough. This would be the point to pop the champagne, but not yet, actually, because the system is not well-posed, turns out. So I mentioned somewhere that you derive this equation by assuming existence of the minimizer and then computing it. As it turns out, the minimizer does not exist. And that's where everything breaks down. So it has to do with the degenerate densities. I mean, it's a bit technical, but basically what it means is that your minimizing distribution will not satisfy your constraints. So there you go. The second thing which appears as a result of that is that you have singularities in the flux. And it's actually worse in this approximation. As you approach equilibrium, the fluxes can become unbounded. So yes, you have a symmetric hyperbolic system. It's almost nice, but it's unbounded fluxes, so the system is not well-posed. And apart from that, there's a real huge practical impediment, is that you would have to compute integrals or moments of exponentials of arbitrary polynomials. And that's infeasible. That's really a complicated problem. You may think that's what we thought initially, we're smart, we can do that. Then it turns out that if you look into this problem, there's heaps of books, people much brighter who've looked into this for years, and they come up with all kinds of, they write books full of approximation methods for this problem, because you really cannot do it in closed form. So there's a few alternative methods. Let me just skip over those. It's a traditional method by Grant. It's actually the original method you would say conceived of in the 1950s. But in general, properties of moment closure approximations. So as I mentioned, it's a Galerke subspace projection. So essentially, it's just a Galerke method. The lowest rank model. Right, so if we take the space to be equal to the collision invariance, we just get the order equations of gas dynamics. So our baseline model will be the order equations. It has a nice hierarchical structure because you have the inclusion relation of polynomials, right? So whenever you crank up the order in the polynomial space, you'll at least include the previous space. So there's a really nice hierarchical structure. And what you can show, at least on some partial results are available that you do get convergence. So if you do increase the order of the polynomial space, you converge to the Boltzmann solution. This has two implications, which are nice, is that it's really in canonical form for a posteriori error estimation and adaptivity. Right? So the hierarchical rank adaptivity would correspond to model adaptivity. And the rank refinement would provide you with the transition between the Euler equations, which is the baseline model, and the Boltzmann equation. So it's really a beautiful model for doing model adaptivity. Just briefly on a new moment closure formulation, because as I pointed out, in principle we have a very nice moment system, but we just cannot use it because it's opposed. So now you have to make minor modifications and see what you can do. And something here which relates actually to the presentation in the opening lecture by Tinsley Oden is that the form is completely given if you adhere to the to Shannon's theorem. Shannon's theorem, we have four axioms, these imply the form of entropy. Which means that if you want to modify the entropy or want to look at a different approximation, you have to sacrifice one of the axioms in Shannon's entropy, and one of the things that we will be sacrificing is actually extensivity. So we're moving to a different approximation with an entropy which is non-extensive. We can discuss that after the presentation. So basically what we do is we want to stay close to the exponential form. We linearize it, you can argue, about a local quadratic form. So the exponential lambda node m refers to quadratic functions. Then we put, so this is basically the factorization of the exponential, and then we approximate the second exponential. So the non-quadratic part, we're going to look into convenient approximations. And one which imposes itself is actually the limit definition, kind of different ones, and you truncate it at some order n. Let's take n2, quadratic polynomials. You cannot take n4, it gets even better, you have to do a bit more work. But in any case, if you take an even order, then you get a non-negative polynomial, which is nice because then you will have non-negative probability distributions. Of course, you need that for oppositeness. The moments of exponentials of general polynomials, which is an intractable problem, is now replaced by high-order moments of Gaussians. That's a complicated problem, but it's doable. You can actually compute these things. So we can really get closed-form expressions of the system if we do this. We still have to think about how we pick the local Maxwellian, right? So the prefactor, the lambda node m, this can be a local or global Maxwellian depending on the problem that we're facing. So just as an illustration, here is illustrated the true exponential and the approximation of the exponential. Near zero, it's really the best approximation. Away from zero, it's reasonably good. It's always positive. It has an issue, we're going to adapt that, but that's basically that the approximation of the exponential will be non-monotonic. Which means that whereas the original exponential decays to zero at minus infinity, the approximation goes up again because it's quadratic. So you get, in that sense, poor approximation of the exponential once you go away from equilibrium. This is not necessarily bad for problems where you're close to equilibrium, but if you're too far away, then you get instabilities. Basically, you do not get any approximation properties, and you do get instabilities. So the modification that we do is actually, we just truncate it here. At the red dot, right, so where we lose the approximation properties, you just truncate it. If you want anything better, you bump up the order of the approximation. You have no options. So, as I indicated already, one of the main issues is that this system will not dissipate our original entropy, but it's because, well, the logarithm is not an inverse of our approximate exponential. That's the property that we use to show entropy dissipation. So the Galerkin orthogonality argument fails. And the idea is that we modify the entropy. Take a slightly different entropy in such a way that, so basically we replace the log by an approximate log, which is the inverse of the approximate exponential. That gives you the approximate entropy, and now you can apply the Galerkin orthogonality argument again. Yeah, so basically, just slightly elaborating on that, what that will give you is, because this entropy dissipation gives you actually the dynamics of the decay to equilibrium. So if we're far away from equilibrium, the dynamics will be slightly different. But of course, I mean, if we get close to equilibrium, then we recover the original dynamics. Essentially, that's what it's saying. So some numerical examples based on the approximation that I just introduced. It's for a 1D shock tube problem. The Knudsen number is 10, so this is a relatively high Knudsen number. We do these are hyperbolic systems, or almost hyperbolic systems, so this calls for a discontinuous Galerkin. At this stage, we do piecewise constants, so P0, forward Euler in time. Of course, you have the system in closed form, but if you want to compute, say, numerical fluxes, solve Riemann type problems, then that's almost impossible for doing that for hyperbolic systems with 8, 10, 16 equations, something like that. You really cannot get the eigenstructure of that in analytic form. So you have to find a flux form, or a numerical flux, which allows you to compute these things numerically. That's the universal ocean type flux. We consider hierarchical ranks up to 3, which is the Euler system, up to 16, which is extremely high. So what we've seen in this field so far is up to, say, 4 or 5, maybe 6. With this new approximation, we can bump it up to 16, and actually the computation for 18, 20, and beyond are running now. It's extremely stable. You can go to really high orders. And as I already indicated, so the baseline system case 3 coincides with the Euler equations of gas dynamics. So that's really the baseline continuum. So this is the setup of the Riemann problem. We have 2 different left and right states, rho, u, and theta, temperature theta on the left are 1/1, and on the right it's half of 4/5. It's a reasonably mild discontinuity, I would say. But this is a standard test case in the literature. What's displayed below is actually the corresponding distributions in velocity dependence, right? So on the x interval, on the left we have this initial profile, and on the right we have the red initial profile. So this is actually what the evolution looks like. Just rewind it, so you can see the original discontinuity, and then you can see the evolution in time of the one part of the marginal. In the horizontal axis we have position, on the vertical axis we have velocity. And what you will see is actually sort of the shearing, which is basically the transport term, and the deformation, that's the effect of collisions. So this is nice. What's actually nicer is to look at this plot, which shows the heat transfer. Why is this relevant? Because our baseline, one thing is that in these systems we would be interested in heat transfer. Okay? And the other thing is that this is really poorly predicted by standard continuum models like Navier-Stokes-Fourier, especially in the Euler system. The Euler system does not provide any description of heat transfer. Right? So the red curve, which is indicated over here, which corresponds to our three-moment system, our baseline model, does not predict heat transfer. It just doesn't do it. It's not part of the model. Now, if we bump up the order of the moments, and you can see that we start to predict the heat transfer much better and better and better as we go up in the order. And ultimately, but that's something we're looking into now, is that you see some form of convergence. So this would actually mean, indeed, if you get this convergence, that you're predicting the heat transfer of the underlying Boltzmann equation. So that brings me to the conclusions. So moment closure systems provide an approximation technique for the Boltzmann equation which have a very nice intrinsic hierarchical structure. They also provide an implicit pathway between, say, the macroscopic model of the Euler equations, the baseline model of gas dynamics, and the Boltzmann equation, or any other kinetic model. It's a very natural transition that you get. We derived a new tractable moment closure formulation based on approximation, or polynomial approximations of the exponential. And something which is most relevant in the context of multiscale modeling is that moment closure systems are really ideally suited as adaptive multiscale models for kinetic theories. They have a very nice hierarchical structure, so it's not really that you go from a simple model to a tremendously complicated one. You can go there step by step by step. It's basically increasing the rate as it's locally needed in your problem. It's a Galerke subspace approximation, so all the theory that we've developed for error estimates for Galerke methods applies one-to-one without any modifications. And the structural properties of the Boltzmann equation, which are fundamental in the approximation, are retained in this approximation technique. What I showed is some numerical approximations based on this continuous Galerke finite element method, and future work will of course be actually the application of error estimates and extending it to multiple dimensions. So thank you for your attention.
Thank you very much, Professor van Brummelen, for this very interesting and inspiring lecture, and also for keeping the time very precisely. Ladies and gentlemen, I don't want to suppress the discussion. If there's an urgent question, please pose it. Also, I'm aware that this is probably not the ideal forum for a very detailed discussion. If you want to pose a question, please come up so that it's easy for the speaker to understand the question. Well, there seems to be no questions, so everything was clear to all of us. Thank you very much.
Okay, well, so that means that next time I ask about the Boltzmann equation, everybody will raise their hand.